Section 4.3 talks about modeling linear trends. So in this class, the only thing we're going to do is actual linear trends. We aren't going to be doing any like that look maybe like a U-shaped or have a curve to them. Okay? So what we're going to try to do is fit a line that fits through the data. Now, we'll not hit every point or may not hit any points, but it's the point that best describes the data. Okay, and what it does is it minimizes the average squared vertical distance, and I'll go over StatCrunch and I'll demonstrate how this works here. Okay, and it's only useful if you do this with a linear model. Okay, so if I head over to StatCrunch, and what I did is I loaded the NBA All-Star Game data, and this is the same data you used for your, I think it was activity 2 that you had to do. If you want to follow along with me, just go to Data and Load, and then choose Shared Data Sets. Type in my name, Burns and Beth, and when you click on Go, okay, choose the NBA All-Star Game data. Okay, so this is the data that I'm using. Okay, under Applets, there's a regression applet that we're going to just do by eye. Okay, so I'm going to use the data from the table. I have my X variable is going to be the winning score of the NBA All-Star Game, and the Y variable is going to be the losing score of the NBA All-Star Game. And now click Compute. So the idea here is you want to try to find a line that fits through the data here. Okay, so I just say, oh, that looks fairly good. If you see this SSE here, stands for the sum of the squared, I thought residuals. Okay, but it just makes it so these vertical distances, the squares of those, and you add them all up, is as small as possible. Okay, this is the equation that makes them as small as possible. We'll talk about that in a second. First, if I go to Options, Edit, I check this box. It says Add Boxes to display squared residuals, and click Compute. Okay, now you see the boxes. And if I move this line around, you can see how the boxes are changing size. Okay. The box is this length here, the length from this dot down to the line, and then it just makes it a square. So you should actually see all these squares. And as you notice, as I move these, right, some of the boxes are getting small. In this case, they're almost all getting smaller. And you can see my SSE number is also getting smaller. So the idea of what we want to do is we want to try to make it so the sum of those squares, or it's actually just the area of all those squares, is as small as possible. Okay, and so then if you click on where it says regression, it actually shows you the actual regression line and then the boxes that go along with it that are actually in red. Okay, so now if we're back on our here, that should make sense here why they're drawing these vertical lines, because they would make a square here with the vertical lines. Okay, and they're just trying to make the sum of the squares as small as possible. Okay, so we can actually calculate this over in StatCrunch. So this is the directions for how to do that. Okay, and if I go back over to StatCrunch again, okay, this time we're actually going to make a graph. Okay, and there's a couple ways to do this. Okay, if we want to see the scatter plot to make sure it makes sense to even do regression on it, I can just choose from the graph menu. I chose scatter plot, and then again I'm going to use winning score and losing score. Okay, if you look here, this display means I actually just want to display the points. That's what you want. But this overlay polynomial order, I can put 1 because a line, it has a polynomial of order. A line is a polynomial of order 1. Okay, this controls how fat your line is going to be, and this controls how big your points are going to be. For a lot of them, you can just leave the same. Okay, and again, there's other options down here at the bottom. You can name and you can label your X and Y axis, which when you're doing your homework, that's actually a good idea to do that. Okay, so when I click Compute, I see the scatter plot along with a line that goes through it. This actually looks fairly linear. Okay. To actually find the equation of the regression line, if we go to Stat, okay, and then there's a regression here, and we're just doing simple linear. So under the Stat menu, I just chose regression and simple linear. Okay, again, I got to select my X variable, which is winning score. My Y variable was losing score. Okay, most of this other stuff we don't really have to worry about it. A lot of it even doesn't even apply to this class. Okay, again, you can still down here label your X and Y axis if you like. Okay, when I click Compute, I get this to start with. Okay, you notice this is similar to the same screen I had with for regression for when I did correlation. I'm sorry, when I did the correlation. So here's the correlation between the two variables, which actually has a fairly strong correlation. Right here's the equation of your regression line. Okay, when I go back to the PowerPoint display, we'll actually talk about what we can do with that. Okay, so that's what you're looking for. If you click the next button down here, it actually does show you the scatter plot along with the regression line. Okay, so this is what we're interested in. Okay, again, you notice it's kind of the same screen I had when I did correlation. I don't care too much about this other stuff. It's mostly just the regression line and the correlation that I'm worried about on this screen. Okay, so now let's go back over here and we can answer some questions about it. Okay, this is actually for a different set, so the numbers are different, a different set of data. Okay, so here's my scatter plot. What if I want to predict the losing score when the winning score is 120 points? Okay, you notice it says losing score equals, and then it gives me a number, plus, and then another number, and this would be times the winning score. Okay, so it tells me the winning score is 120 points. I'm going to put 120 right in here where it says winning score. Okay, multiply it by the 0.8626, which this is the slope, and then add in, this is what we call our y-intercept. Okay, so I get 110.7. Okay, but I can't score 0.7 of a point, but it's actually an average, so you can either say 111 or 110. Okay, so what this tells me is if the winning team in the NBA All-Star game scores 120 points, then the losing team is predicted to score 111 points. Okay, so I can make predictions based on my regression line that I've put in. Okay, so the slope is the coefficient in front of the x in the regression line. Okay, if you remember, if you remember some of your algebra, slope is your rise over your run. Okay, so it's how far you move vertically over how far you move horizontally. Vertically being the rise and horizontally being the run. So if the run is increased by 1, then the rise, or your y, is predicted to increase, by an average of the slope value. Okay? And the slope is only meaningful if the data follows a linear pattern. Okay? So back to my example here. Okay? In this case, what's my slope? It's the number in front of what they call the independent variable, which is the variable that's on your horizontal axis. So that's the 0.86259814 number, or we can do a little bit of rounding, so 0.863. Okay, so how can I interpret this? It says, so if x is increased by 1, because remember you can take any number and put it over 1 and it doesn't change it. So my rise over my run, the rise will be 0.863, the run will be 1. Right? So if x is increased by 1, then y has an average increase of the 0.0863. Okay, but it's better if you could interpret this in context of the problem. So what does it actually mean to say this? So for every additional point the winning team scores, the losing team will score an additional 0.863 points. Okay, so that's an interpretation of the slope in context of my problem. Okay, so x is always increased by 1, and your y is going to have an average increase of the slope. Okay, how about if I want to interpret the y-intercept? So remember, a y-intercept is the value of y when x is 0. So it gives you the value of your variable on your vertical axis when your variable on your horizontal axis is 0. Okay, so it doesn't always make sense to interpret the y-intercept. If you have no values that are close to x for 0, if you have no value of 0, let me start over. So if your x's aren't anywhere close to 0, then you shouldn't be interpreting the y-intercept. It doesn't make sense in context of your problem. Okay, so the calculated y-intercept value is meaningful only if you have the values close to 0 for x. Okay. Okay, so again, here's my example. In this case, what's my y-intercept? Okay, well, it's this number here, and the way this writes, it's at the front, so it's 0.716601, or again, we can do a little bit of rounding. Okay, so that means if the winning team scores 0 points, then the losing team is predicted to score 0.7166 points. But does this make sense? And you'd say, well, the winning team's probably never going to score 0 points. If you look on your graph, my winning score is never even close to 0, right? And also, if the winning team scored 0, then the losing team scores almost 7 points, then the winning team is actually the losing team. So all of this makes no sense to even talk about in the context of this situation. Okay? So here's another example. You have a sample of high school freshmen and sophomores, and you get this regression line. Okay? The y-intercept is this negative 9.2. Okay? So does it make sense to try to interpret that y-intercept? First, you can't, for a person, you can't really have a negative height. This sample only includes teenagers, high school freshmen and sophomores. Okay, so my age of 0 years is too far away from the age of these freshmen and sophomores. So this is another example where we should not be interpreting the y-intercept. Okay, I can interpret the slope. Okay, so the slope is 4.9. It's the number in front of your x, and this x actually will actually be the age, or it's an equation that relates age to their height. So the predicted height is, and I can put age right here. Okay, so high school freshmen and sophomores grow an average of 4.9 inches per year. So if x increases by 1, so that means if their age increases by 1, then their height's going to increase by the slope, which is 4.9. Okay, another thing just to remember is that correlation does not mean causation. So strong correlation is not evidence of a cause and effect relationship. Okay, remember, the only way we can actually get cause and effects is if we have a well-designed experiment. Okay, and a lot of times when we're looking at relationships on scatter plots, we're just looking at doing some statistical analysis, and a lot of times they're even only like observational studies. Okay, so when you're trying to describe things, don't use the word causes, makes, will, because, okay, because those imply causation. Okay. You can talk about it predicting in tens and on average. Okay, so here's another example. Okay, the predicted salary is 22,000 plus 8,000 times the number of college years, or how many years you have been in college. Okay, you shouldn't say each year in college results in an additional salary increase of $8,000, because that makes it sound like you have some causation. Same thing, a person with 1 more year college education will earn an extra $8,000. Remember, my predicted salary is more of an average. The correct way to say it is, on average, people with 1 more year of college education tend to earn an extra $8,000. If you remember with correlation, if you switch to the x and the y, it didn't change the value of the correlation. Okay. But it does change the equation of the regression line if you switch your x and y around. Okay. And the other thing is, if a linear model is a good fit for the data, then the mean value of y for each given x will nearly lie on the regression line. So if you look, here's my regression line through here. If I look at all the heights at 65 inches and find the mean of these heights at 65, or I'm sorry, this is weight in pounds. If I find the mean weight of everybody who had a height of 65 inches, that point should be close to your regression line. If it's not, then chances are you shouldn't be talking about the regression line. Okay. Same thing here. I could move up to 70, find the average weight of everyone who's 70 inches tall, and that point should fall fairly close to the regression line. So the regression line is saying what we think the average is going to be of people whose height is 70 inches, what we think their average weight will be. Okay. And just as we finish up here, this is an interesting graph that I found, and it just shows how as the gas prices increase, right, presidential approval ratings seem to be decreasing. Again, there's no cause and effect here. It's just an interesting relationship, but you can't say that gas prices are causing the president's presidential approval rating to decrease. We can't say one causes the other.